Lesson 4.2, Isosceles and Equilateral Triangles. This is one of those critical lessons that requires a lot of thought and a lot of application between now and the end of the school year. So you have to learn this lesson. Anything that you're not sure of, stop the video, pause it, go over what was just discussed, do the practice problems, okay? So the tool shown shows a triangle with two sides of equal length. So there's two sides of equal length and an outline of the triangle. You can drag and drop it. So I'm going to show you how this works. Here's the front of the triangle. And as I rotate it, see how the numbers, like number 3 is rotating that way. These are going counterclockwise. And I'm doing it quickly so you can't see the actual pattern. You'll have to go through it slower on your own. And here's a flip or a reflection. If you're reflecting right from that point, that number 1 straight down, it's like the reflection right to there's like the mirror, the line of reflection. And then there's the back. Okay, so it says, in how many different ways can you flip, slide, or turn the original triangle? So it fits exactly on the outline. So that means it's mapping onto itself. So drag and drop, you're looking for relationships. Example 1, understanding isosceles triangles. You should have learned about isosceles triangles years ago, but isosceles triangles are those triangles that generally you see that have like there's a nice, tall, skinny triangle like that, but it doesn't have to look like that. It could be like a really big, obtuse triangle. Bottom line is isosceles triangles have two sides that are congruent. Those two sides come together at a point. That point that creates an angle, that is called the vertex angle. Okay, so we're going to be talking about a lot of isosceles. How are base angles of an isosceles triangle created? Now, this is a great thing to know because these two sides are congruent, the whole definition of an isosceles triangle. But what this explains is that if two sides are congruent of a triangle, the two base angles are also congruent. Now, we're not talking base like the bottom. We're talking base like across from that vertex point that I was just telling you about. So this is the vertex point where the two congruent sides come together. So point B is the vertex point. And then these other angles, A and C, those would be the congruent angles. So this says, because BC and BA are congruent, BC and BA, you can map using a line of reflection right here. And it even tells you that. And so this angle that's created ABC is created and it's being cut directly in half or being bisected. Okay, so these two sides of the angles are congruent. And it says, note, the reflection across BD of point B. So look at point B. If it reflects across this line of reflection, it's not moving. And that's what that says. Same with point D. If it's on the point of reflection, it's not moving. So D reflects onto point D. But BC would reflect across to BA. And BA would reflect across to BC. And all of that would result in these two angles being the same. So if it's an isosceles triangle, you have a triangle that's isosceles, the two base angles are the ones not touched by the two congruent sides. Those two base angles will be congruent. And here it has you actually construct this one. Remember, we have to go back way back to topic 3 when we did reflections, rotation, translation. It says in an isosceles triangle, BC, so this side is congruent to this side, BA, so that this is the vertex angle. These would be the two congruent angles, just like the previous picture. What rigid motion would map this new triangle if it was reflected across BC? What would map it? So it wants you to actually construct it. And remember, when you do constructions, it's best to enlarge this. So I blew up this the screen. And if you remember how to reflect, you need a line right here. You need a line here as the line of reflection. And then you need to create perpendicular lines to that. So I'm going to first start here just so you can see the long line. I'll go from these 2 points. So then you can see this line of reflection just really big so it doesn't interfere with the actual triangle. You can see the whole thing. And then I'm going to make a line perpendicular to that line. So perpendicular to this line going through point A. Because if I'm reflecting this triangle to over here, BC isn't moving. This segment is not moving because it's the line of reflection. But point A will reflect over here. And I can't remember if you remember, or I don't know if you don't remember, but this point from A to the line of reflection will be congruent to the line of reflection to point A prime. So I'm going to make a segment from this point A to there. Just so I have a segment there, that's going to be my radius, okay? The actual radius of the circle. I'm going to get my compass, and I'm going to say, I want a radius this big, that segment. That's the whole reason why I made the segment. So it matches the radius, and I'm going to move the center to that point on the line of reflection. Notice the circle is as big from the line of reflection to point A. And then I need to get a point right here. This point is A prime. That's the reflected version of that point. Now I'm going to grab my segments. Here's A prime to B, A prime to C, and that is reflected. I'm going to change the color. Oops. Click on it first. Now I'm going to change the color. And you can highlight more than one thing. I'm going to get rid of this circle just to get it out of the way. And I have a reflection. In fact, I can get rid of this too to clean it up a little bit if that helps. And this was just the segment, the radius. So hide anything you want that will help. So here's the original or pre-image, ABC. Here is the reflected image, A prime, B prime, C prime. So let's go back and practice using those tools. They really help to help you get better for later when we do more constructions. Okay, I'm going to shrink this. And it says, what rigid motions map the prime version back onto the original or pre-image? You're going to show or explain why angle A is congruent to angle C. Now, we just reflected it. So, of course, you can discuss reflection back. There are more ways to map it on besides just reflection. So I want you to think of the different ways, and you can check that answer here. Isosceles triangle theorem and the converse. So there's the theorem and the converse. And in that previous lessons, we said if there's someone wearing shoes, they're wearing converse. Here's the if, then the converse is switched. So for example, here is the rule. Isosceles triangle theorem says if AB is congruent to BC. So if it is an isosceles, you have two sides that are the same. So if two sides are the same or congruent on a triangle, I slide down a little bit, then the two base angles are congruent. So ACB, that's that first one, and then BAC. BAC, notice the middle letter is the vertex, like the actual angle where it opens. So since or if the sides are the same, then the angles are the same. If the sides are the same, then the angles are the same. But then the converse, which is this one, if the two angles are the same, then the side lengths will be the same. So isosceles triangle, if the two sides are congruent, makes it isosceles, then the two base angles. Converse, if there are two base angles that are congruent in a triangle, then it makes it isosceles or makes those two sides congruent. So using that theorem, so what's the point? We know this theorem, so what? So look at this map. First of all, look for any degrees. I see a 50 right here. And I see these tick marks. So this is applying the isosceles triangle theorem. So you have tick marks, you have degrees. And so basically, this is the isosceles triangle. It's tilted, whichever way there, that way on your camera. It's tilted, so angle D, or that 50 degrees is right here where my fingers are touching. And you need to find these other two angles. So let's think about this. Now, while I'm sharing, I'm going to shrink my screen a little bit. And I want you to look right here. So I have this, and I'm tilting it a different way, but that's okay. I have a 50 degree here, and I have these two angles, which I should know are congruent, because if this is isosceles triangle, then these two base angles are congruent. The theorem says that these two triangles will be congruent. So we're like, okay, they're the same, but what are they? And that's when you go back to the triangle sum theorem. So everything that you do in math, there's a lot of algebra in this textbook, but you have to think back to the rules. So because of the isosceles triangle theorem, those two are congruent. So I'm going to say isosceles triangle theorem. That's the abbreviation for theorem. But that doesn't help me solve. If I need to actually solve for these, I'm going to look back to triangle sum theorem. So I'm going to say triangle sum theorem. And that means that all the angles of a triangle add up to 180. So I'm going to just call these x. Since they're both equal or congruent, I'm going to call both of them x. And I know that the rule says all the angles of a triangle add up to 180. So all the angles of a triangle add up to 180. Think of the rule and write the equation based on the rule. All the angles of a triangle equal 180. Now you solve it. So I'm going to subtract the 50 on both sides. So, and actually, I'm going to put these together too. So I have an x plus another x. That's 2x. I've got 180 minus 150, and you get 130. And I'm hoping at this point you know what to do. But if you don't, you have a variable touching the x. Touching means times, so you undo it by dividing. Okay, and just for fun, I'm going to make you figure that out. Okay, so that's how you do it. Think of the isosceles triangle theorem. Think of the triangle sum, add them up to 180 to solve. So let's go back to that problem. And it says, to protect the landscape of this minimal erosion, what angle measure should the architect specify for the corners in her design? Now, we just went through almost every step except the last one. I want you to try to do this by yourself. Now that you can't see it, cover up the works, pause the video, and do this all by yourself and see what you get for your final answer. Here's another one. Try it. Now, again, be careful. I need the x, but I don't have very much here. So I'm going to go to my paper. I'm going to draw a picture. And anytime you have especially algebra involved, you write it down. Because honestly, most kids are going to make the mistakes not in the actual theorem, like the triangle sum theorem or the isosceles triangle theorem. That's not where they're going to make the mistakes. They're going to make the mistakes in the algebra. So here we go. I'm going to switch my screen again. And I've got, here it is, light it up. This is what I've got. I've got this 5x plus 9. I've got the 28, and I just want to double check where my tick marks are. Yep, here's my tick marks. Right here and here. And as long as they match each other, they are good. So I'm going to go back to this. And notice, put the tick marks. I put double tick marks, but only because this one had single up here. And since I'm on the same paper, I don't want you to think they're the same as the previous problem. So what do you think I should do? These tick marks mean something. And by the isosceles triangle theorem, that should tell you something about these angles down here. Those should be the same. So if this is 28, this is 28. So that's 28 degrees. And then I think, okay, well, I've got 28, so what? I need to solve for x. So then I think triangle sum, 5x plus 9 plus 28 plus 28 equals 180. Do this every time. So to be good at this, and especially to get good at proofs, I'm going to write isosceles triangle right next to the 28. That's how I knew it was 28, because of this rule. Theorem, isosceles triangle theorem. THM is abbreviation for theorem. How did I know this 180? There was never a 180 in this problem. Well, I knew that because of the triangle sum. So triangle sum theorem. Every single time you come up with a number or a process in your problem, you write down the rule, because it will save your hiney when it's time to do proofs. So, and then you're going to solve. Combine like terms. Notice I'm not doing it for you. You'd have 5x plus whatever that is equals 180, and go from there. Try that one. Check your answer when you're done. All right. This next one, same idea. And I look at this and I'm like, okay, I got the tick marks. I got these two things, and I have nothing right here. Okay. I can't solve for this third angle if I don't have anything. So I can't say this angle plus this. I can't add these up and equal 180. So then I'm like, what do? I do know that because these are isosceles, an isosceles triangle, these two are the same. Well, if something's the same or congruent, doesn't that just mean equal? So what I would do on my paper, and I'm going to write it down and then I'll show you. If I know they're congruent, I know they're equal, I'm going to set them equal to each other. So look at this. Slide it down a little bit. Here's that first angle. Here's that second angle, or left and right. I know they're congruent, so set them equal to each other. Congruent is saying that the measurements are equal. So you're going to have to get the x's together, move them, get the constants together, and then solve for x. So in this case, you don't actually use the triangle sum. So really watch those things. You might not use all the theorems you know. You might use some, and they might just mix and match. So just watch out for any rule that you have learned so far is fair game in all of geometry from now on. That's why learning those rules and using those flashcards that I created are super important for you. Okay, using the converse. Well, then you're like, ooh. We know that triangle sum, like the angles add up to 180. And I know these angles are the same, but these side lengths, they have nothing to do with 180. 180 only is associated with the angles of a triangle. So it doesn't tell me the perimeter, because if I added all these up, it would be the perimeter. So I look and I'm like, oh, there's got to be another way. But then I think of the converse. The converse says if the two angles, or there are two angles in a triangle that are congruent, that means these sides are congruent. And I just told you, if something's congruent, you set them equal. So this doesn't help me at all right now. But this, I know these will be equal, congruent, because these side lengths, so the converse is, the angles. If the angles are congruent, then those side lengths are congruent. So I'm going to set up, and I'll show you the picture again. I'm going to have x plus 20 equals that 8x over 3. So I'll show you what I wrote. Here it is down here. X plus 20 equals, because they're congruent, 8x plus 3. And for some of you that hate fractions, you can either make this all a fraction over 1 and cross multiply, or you could just say multiply by 3 on both sides, and these would cancel to help you get rid of that fraction. All right, so that will help you get started, get the x's, solve for x. And if I look back at this problem, it says, what is the length of all three sides? Well, once you solve for x, then you have to plug it in. So this problem just gets more and more difficult. First, you have to set up the sides equal to each other. Then you have to set up or solve for x. Once you get x, then you plug in x to each of these side lengths. And again, you can go through and check every single step of your answer over here. Okay, what is the value of x? This problem is almost identical to the one that we just did, but it's breaking it down for you. So you're going to try this by yourself. Two angles that are congruent. Think about what theorem. Is it the theorem or the converse? And then once you know this, can you use that variable or solve for that variable and then plug it back in, because then you're going to need the side lengths. All right, next theorem. This theorem it's a little bit like intuitive, like it kind of makes sense, but some kids just don't think it's a theorem. So there is a theorem that explains this. So it says, if a line or line segment, let me get this out of my way. If a line or line segment bisects the vertex angle. So here's that vertex angle that I told you where the two congruent sides come together. So 4.6, 4.6. This angle, if it is bisected, see how they're exactly the same? Every single time on a triangle, that angle bisector will create a perpendicular bisector. So if I bisected this vertex angle, the line that is bisecting this angle creates a perpendicular line, 90 degrees, and cuts the bottom perfectly in half. So that theorem, which doesn't really have a name, it's theorem 4.2, you can't say on a proof, theorem 4.2, because that doesn't make sense to anyone except they're using this textbook. So you would have to explain, if a vertex angle is bisected, then these two are congruent segments and it creates a 90-degree angle. When we get to proofs, I'll explain more about that. But for now, just be aware, if the vertex angle is bisected, it creates a perpendicular bisector of that base or that other side. And this is explained step by step here. And you can even manipulate it more as you want to, like anything to kind of just see how it goes. So now we're going to use that in our actual application problem. I love this problem. This is a real world problem that you can already apply what you've learned in so far in geometry. A prefabricated home. It's a like a double wide trailer or a mobile home. So it says is delivered it to a foundation in 2 symmetric halves. So right here, see how it's a double wide means there's 2 pieces and they puts together. So right here at point B, all the way straight down, it actually, and you may have seen these delivered on a truck, it separates and each side goes on a different, like big semi truck. It says there is a clearance under a bridge of 17 feet. You need to determine if this will fit under there. So this is what I would do. I would break it up into rectangle and triangle. Okay. And the solution actually shows how it is. I'm going to draw it on this paper just to help you see it a little bit better, and then we'll walk through it as we go. And again, my drawings are never perfect, but hopefully you get the idea. 16, I'm drawing this, 10, and this is 20. And these are all feet, but for time, or 28, sorry. For all time's sakes, I'm just going to, I didn't label all the feet. So here we go. I've got this sketch kind of picture, and I need to figure out if this distance from here to here can fit under a 17-foot bridge. There's my bridge. It's a really ugly bridge, but there's my bridge. Okay, bridge. Can it fit under there? So we have to figure out the height. I know this is a rectangle. This is 10, so this is 10 right here. So I've already got a distance of 10 feet. So I hope this distance right here is 7 or less, actually less than 7, because if it's 7, we're still going to hit that bridge. All right, so how do we figure this out? I do know that these angles are bisected because the problem told us. So those 2 angles are congruent. And if these are congruent, it creates a perpendicular bisector. Well, I don't know this length, but actually I do. If this is 28, this whole thing is 28, which means this side would be 14 and this side would be 14. And I'm going to highlight just this part right here, just to see. Do you see that right triangle that I just highlighted? That right triangle, think about what I'm saying, right triangle, I'm going to bring out here. I've got a right triangle that's 16 feet over here, 14 feet over here, and I do not know this length, that height. I'm really hoping you remember the rule that helps us find that height. Let's see if this helps. Pythagorean theorem. You're going to have to use the Pythagorean theorem. A squared plus B squared equals C squared. And see if your x, once you solve for x, if it is less than 7. If it's less than 7 to make a total of 17, then you're good and it fits under. If it's more than 7, that's not going to fit under the bridge. So feel free to use the solution, go through step by step. But the reason why we can solve this is because we know if this angle is bisected, then it creates a perpendicular, right here, there's 90 degrees, bisector. And that's why we get this 28 cut in half perfectly, 14 on each side. And it's having you do some other examples to check. This one's, they don't give you step by step, but this one says find the measurement of RSQ. So RSQ, it doesn't give you the measurements at all. But think about it. You know this is an isosceles triangle, which means by the isosceles triangle theorem, this angle and this angle would be the same. So the side lengths are the same, so those angles are the same. So 31, 31, and then you're like, well, I don't have this whole angle. But by the triangle sum, 31 plus x equals 180. Once you get x, then you could divide it by 2 to get each half. So you're going to use the isosceles triangle theorem. If the side lengths are the same, those angles are the same, 31, 31. And then the triangle sum, 31, 31, this angle, it's upside down, but this angle, you could subtract. So 180, 31, 31 plus x. And you'd have to subtract to solve for x. And once you solve that, divide by 2. And then it asks you for an actual side length, PR. And I am hoping you can do that based on the theorem we just went over, like with the mobile home. Okay, because if that top angle is bisected, it creates something at the bottom. That's a little hint, a perpendicular bisector. So equilateral triangles. If the angles are the same, then the side lengths are the same. Now keep in mind, we've been doing isosceles triangle. Now we're doing equilateral triangle. And those mean all the side lengths are the same. That's usually what you're taught up until this grade. But what I'm telling you is if the side lengths are the same, the angles are the same. And if the angles are the same, then the side lengths are the same. Now keep in mind, I'm going to show you this on the next slide. But if I cover this up right here, this little tick mark, let me cover it. That's just an isosceles triangle. And we already know that if the two side lengths are the same, those two angles down here are the same. Okay. Now if I cover this one up, then it won't let me cover it up all the way, but pretend like that's gone. That's an isosceles triangle over here. Those two side lengths are the same, which means those two angles are the same. So it's basically an isosceles triangle multiple times if I rotated it. So these, depending on which line I cover up, the tick marks, they're isosceles triangles, but they work for everything. So since all the side lengths are the same, all the angles will be the same. Okay, this theorem is going to explain what I just explained, that if the side lengths are the same, the angles are the same. So by the isosceles triangle theorem, DF and EF are congruent. Therefore, these angles are congruent. And DF, DE, if these side lengths are the same, then those angles are congruent. And by the transitive property, if they're all congruent to the same thing, they would be congruent to each other. So the conclusion is, if the three side lengths are the same on a triangle, the three angles are congruent on that triangle. So you're going to prove the opposite. You're going to prove if the angles are the same, then the side lengths are the same, basically the same way. So it says by the converse of the isosceles triangle, because that's the converse, you start with the angles. If angle G and H are congruent or the same, then these side lengths are congruent. If angles G and J are congruent, then GH and JH are congruent. And again, kind of by the transitive property, how if they're all congruent to each other, then if one is congruent to one angle, one is congruent to another angle, they're congruent to each other, and side lengths, then it basically says all the side lengths will be congruent. Okay, you're going to try this by rotation. You can move this point of rotation. So if I want to rotate this way, it says use the tool to rotate DEF around point P. So if I rotate it, you're like, okay, rotate, 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 rotate. Doesn't help me see how the angles are congruent. So you might want to move this P around and see if it can help you recognize that something is mapped onto itself. That is a hint, and see what you can find out with that one. Finding angle measures in isosceles and equilateral. So you are actually going to do some calculations. I've got my paper ready to help you out. It says if angle CBD, remember the middle letter is the vertex, CBD is 130. So give me a second to draw this out. And again, oh my goodness, my drawing is terrible. You'll get the idea though in a second. All right, so let's check this. CBD is 130. Okay, I hope you can draw better than I can. CBD is 130. I'm like, oh no, that's all it says. I have ridiculous amounts of measurements and tick marks, and I got to figure this out. So first, I'm going to highlight something. I'm going to highlight this triangle only. I am hoping you can see that this triangle has 3 tick marks. because we just learned that equilateral triangles will all have equal angles, which means it's an equal angular triangle, I'm going to put little arc marks right here, here, and here. So I don't know if you can see those pink ones, but remember the triangle sum, it said all the angles in a triangle add up to 180. I'm going to call these all x, 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 x. So I have x plus x plus x equals 180 because of the triangle sum. Well, combined like terms, that's 3x equals 180. Divide by 3 on both sides. X equals 60. This is a good thing to remember and possibly memorize. In an equilateral triangle, all the angles will be 60 every single time because 180 divided 3 ways is going to be 60 every single time. So this picture's getting a little ugly. Let me draw it again. Maybe I'll even draw it better this time. It's a little bit better. So here's the B, C, D, A. I just calculated that each of these angles are 60, 60, 60. But then from prior knowledge, or like the given of the problem, we were told this angle right here is 130. Put a little arrow, 130 degrees. And the question asks for us to find, let me look, to find BAD. So I'm like, oh my goodness, that's not even the angle I'm talking about. But I can get there. I need this angle down here, but I'm going to need this angle first. So you have 130 degrees. You have a 60. I'm going to put this as a y. So I have 60 plus y equals 130. I know that these two angles added up together should equal 130. Now, how do I know that? You can say it a couple different ways. It's the angle addition postulate. Some people just describe that when you have two angles added up together, it will equal the total. But on a proof, you could explain it either way. So basically, I know this because two angles that are adjacent will add up to the total angle by angle addition postulate. So I'm going to say minus 60 on both sides, and you will get y. Notice I'm not giving you the answer. Okay, once you get y, you're going to plug it in here. And I'm going to highlight something again. See those tick marks? If I knew the measurement of angle y, I'm hoping you can get these two angles because those two angles will be congruent because this is an isosceles triangle. This green one is an isosceles triangle, which means this angle and that angle will be the same. So without giving you like answers, I'm going to call these both z. Z, z. So I know by the triangle sum that y plus this z plus this z equals 180 because the triangles add up to 180. So once I get y, I'm going to say y plus z equals 180 because of triangle sum. And I'm going to solve for that angle there. And they want this measurement of z because that was the question. And then I would know it. I would plug in y once I get it, but I'm not giving it to you. And then you would subtract that number from 180 on both sides. So you subtract that number, z plus z, 2z equals whatever you get from 180 minus your y number that I can't tell you because I'm trying to see if you can get it as much as you can. All right. Next one, this one, same idea. The solution is there. Tick marks are there. Be careful. This is not equilateral, but it is isosceles, which means this angle here and that angle there will be the same. So let's just say x. X plus 72 equals 180. And then go from there. But there is a different rule in here. Right here at this point V, once I get this angle, you have to figure out how to get this side, this angle. So be careful. But I think you know, this is a straight line. So if you have a line and one angle coming off of, or a line coming off of it, these two angles adding up together equal something. I'm hoping you know. If not, it's 180. So when I get this answer, x plus 72 equals 180, I solve for x, and I'll have that number right here. Then I know x plus this, we can say y. X plus y equals 180, and solve for y, because it's a line, a linear pair, or angles on a line. That was a lot of information. Stop and rewind if you need to watch the video again, but that's a lot. So isosceles, these base angles would be the same. And then a linear pair, this measurement that you just calculated, plus this other measurement, which we don't know, should equal 180 because of a linear pair. And then once you know this, then you go back and say, okay, this is also an isosceles triangle. So again, go step by step, see if you can calculate, and the solution is here if you need it. And here's one that you're going to do completely on your own without any like step-by-step instructions, but you can check your answer. Okay, lots of information. That was probably the biggest lesson we've had so far. So isosceles triangle. If a triangle is isosceles, then the base angles are the same. Okay, which this is the isosceles triangle theorem. If the sides are congruent, then the angles. The converse would be if the angles are congruent, then the side lengths are. Perpendicular bisector rule. If you have a isosceles triangle that's bisected, the angle is bisected, right here, the vertex angle, then it creates the perpendicular bisector of that opposite side, perpendicular bisector. And then equilateral triangle, if the triangle side lengths are the same, then the angles, the converse of that would be if the angles are the same, then the side lengths would be. That is a huge lesson. Please go back, rewatch as many times as you need to, and do all the practice problems, because this is one of those lessons that will come back all year long.